Hey, I'm Ted. Welcome to another Skoolie video. Today I'm with my friend Tony, Professor de Blasi, who teaches automotive electrical. So we're going to look at 12 volt, 100. We're going to look at electricity today as it relates to the Skoolie. Okay, so today we're going to talk electrical terms and some basic concepts. So we're going to look at AC, DC, how electricity works, and circuits, something like that.
I like to start with, why are we using electricity? Right? Why do we even have it? What's the point? We use it to do work, right? To work. So electricity is a term that we use to describe a variety of things that happen from the flow and result of electrical current. That's what we're trying to establish. So we use electricity in a vehicle. And I'll kind of be referring to my PowerPoint that I'm using right here that you'll play in the corner of this thing. So we use electricity in 4 different ways. We use it for heat, we use it for light, we use it for magnetism, and we use it for network communication. And
with us too, so we're going to be dealing with 2 different systems. We have the electrical system that runs the bus engine and those types of things, like typical automotive. Yep. But we'll also have electricity to run like the domestic stuff, actually in the bus.
Yeah, aftermarket stuff as we refer to in the automotive world. We call that the aftermarket.
The aftermarket.
So custom. Yes.
Schoolies are all about aftermarket.
All about
everything.
Custom. Yeah, absolutely. So and this information applies to that because really you get to build your platform. You don't have to learn someone else's platform. You get to build it from scratch, but you have to follow certain rules. Right. Right. And that's, I think what helps is if we establish what kind of the rules are, the fundamentals of electricity will help you establish those rules.
Right, and hopefully, and one of the goals is that we understand these concepts and don't get so overwhelmed when we think about the whole system.
Yeah, because it can be overwhelming.
Yeah, for sure. Awesome.
So I like to start explaining electricity in its smallest form. So we're going to start here at the atom. And the atom contains everything we need to basically make our electricity. Okay. So really, we everything we see, touch, breathe, everything's made of atoms. You're made of atoms, I'm made of atoms. Specifically, the atoms we're going to be working with are arranged a certain way. And when I talk about atoms, we have to kind of discuss what the different parts are. And in the center of the atom, we have our proton, which is a positively charged particle. In the center, we also have neutrons. They don't have a positive or a negative charge. They're just simply in the center, taking up that space. But that doesn't really apply to what we're doing or apply to electricity for what we're doing here. So we have all of our protons and neutrons in the center. In this example, we're going to be talking about a copper atom. So there's going to be 29 protons. So there's a specific number. Orbiting that nucleus, we're going to have electrons. And these electrons orbit on different levels. That's not really important. The only thing that's really important is this little fella out here on the end. I'm pointing at it, but you can see this little fella out here on the end in the upper right-hand corner. He is the one, he's all by himself, and it can be shared easily. And we call that a free electron, while all the other ones are bound electrons. So this is important, and I'll show you in a moment what I mean by this. Its number is 29. If we follow this copper atom to our periodic table of elements, with everybody cringes when they see this from high school.
No, it's hideous.
It's terrible. Oh my God.
Oh, the horror.
This little number here, that 29 is the number I'm referring to, with the 29 protons, 29 electrons. If that's the case, the copper atom's happy. Nothing. It's balanced. It has no reason to give us any electricity. We want to get the electricity out of it. So what I like to do is talk about angry atoms or pissed off atoms. So our angry atoms are positive atom or negative atom, doesn't matter which. When we anger it, we're basically changing that balance. So in this example on the top, we have 2 protons and 1 electron. It's not happy. It wants to be balanced. It wants to be 2 and 2. The one on the bottom, it has extra electrons. So if I were to put these 2 atoms in the same room, that electron from the negative atom would move over to the positive. And that movement of electricity would give us our heat, our light, our magnetism, and our network communication.
And that's current?
That would be current. Current flow. So we're going to get into what pushes what current is and what resistance is as well. So in this example, I like to always say this is my electron microscope. If I was able to get down in and actually see it, and that's one of the things with electricity, it's invisible. In this example, our free electron, as you can see on the bottom, is just kind of hanging out. It's just chilling, right? There's 29 protons, 29 electrons, everything's happy. Well, along comes a disturbance And that disturbance is going to be represented by this force. And I represented it with a boxing glove.
A disturbance in the force.
A disturbance in the force.
Oh no.
So now we have 29 protons and 28 electrons. We've just turned that into an angry atom, right? So it's not happy. So we need to follow where that electron went. So he's like a billiard, like ball, playing pool. It's knocking these other electrons off. And as we zoom out, it's kind of like a flash mob of electrons all moving down this wire, creating current flow, right? So we have all of this material moving across this wire, being pushed by this unseen force, and that unseen force would be this plunger. And that plunger, we would refer to that as our voltage. Okay, so the voltage is the force that causes the electrons to move. If we don't have enough of it, they're not going to move, right? If we have too much of it, they're going to move really fast. So it's going to alter, right? So the other pieces of the puzzle are we want to have our current flow. We want to be able to measure that, and that's our amperage. Now, if I was to draw an invisible finish line anywhere along this wire, and I was able to measure or count how many electrons are going by, if I could count 6.28 billion electrons over the course of 1 second, that's known as 1 amp. And that's a lot. That's a significant amount of current flow. So that is how we get 1 amp. Now this light bulb is our resistance. That's the reason for the circuit. We don't just build circuits with a battery and wires. We want to have a load too. So that light bulb would be our load, and that's resistance, and we measure that in ohms. So that is essentially what the trifecta of electricity. And that's what you really need to understand before moving forward. So now that we have those locked in, let's show you the dead scientists, or the dead guys that we named these after. We have Alessandro Volta on the left. Alessandro Volta, who we named volts after. He made the voltaic pile, which I think he made his battery out of beets and zinc and if they had pennies back then, they'd copper.
Bring back beet power.
Beet power. So he basically was credited with that, or his name went to voltage. And then we had André Marie Ampère. He was a French physicist who had a lot of breakthroughs with electromagnetism. They named the ampere after him, or the amp after him, and he is known, or it's a column of electricity, that's 6.28 billion electrons passing that given point. George Simon Ohm is a rock star. That guy is the man. He was a professor in Germany who came up with our Ohm's law that we use. So our volts divided by amps gives us ohms, our volts divided by ohms gives us amps. It's the formula that we use to kind of predict what the other is going to be. Essentially, Ohm's law is amperage is the result of volts and ohms. So if we have a certain amount of voltage and a certain amount of resistance in a circuit, we can just use his math to tell us how many current or how many amps are going to flow. So we call that Ohm's law. Super, super useful when we're dealing with electricity, especially if I'm building an aftermarket system. I need to know my ohms.
All right, so we're going to talk about resistance.
Yes, so we'll talk a bit about resistance. Normally in an electrical circuit, if you lower your resistance, well, this is fact, when you lower your resistance, you increase your ohms, right? So in this example, I'm using a seesaw. In a Skoolie application or an automotive application, you have a fixed amount of voltage, right? You have 12.6 volts at your battery when the engine's off. You have 14 and then something, 14 point whatever volts when the engine's running. That's your alternator's voltage. And you also have a fixed amount of resistance, because the light bulb that you have or the motor or whatever you have is a fixed amount of resistance.
And the wire gauge.
And the wire gauge, it's all the same. It hasn't changed. So because you have a predictable amount of voltage and a predictable amount of resistance, your amperage is, because it's a result, is going to be predictable. So you can know how many amps are going to be drawn. As you start to add more things onto this circuit, you're getting less and less resistance, and this kind of goes to parallel circuits, but when you add more things on, less and less resistance is going to keep increasing your current. So when you build your circuit, you have to build it thoughtfully. You have to build it to the right gauge, as you said. You want to make sure that your battery can hold up. You might want to add additional batteries in parallel. We can get into that later. But it's important to understand these fundamentals before you begin this. So here's another example where as we increase resistance, amperage goes down. This is where I like to use the analogy or example of a dimmer switch or your stereo volume. Either one works. So when I turn my lights down, I dim them, I'm adding resistance. If I want my lights to be brighter, I decrease resistance so my lights will get brighter. Same thing with your stereo. As I turn my volume up, I'm decreasing resistance, allowing more current to flow to my speakers. When I turn the volume down, I'm increasing resistance, allowing less current flow to my speaker. So it's kind of, when we talk electricity, this is where it gets confusing. We're kind of talking backward speak. We're talking like Yoda. Right. You know what I mean? So it's can get very confusing very quickly. So Ohm's law, the way that George Simon Ohm wrote this law, was that it takes 1 volt of electrical pressure to push 1 ampere of electrical current through 1 ohm of electrical resistance. That's the law at its purest form, right? The basics of of how we do things. So in this example, I'm actually going to plug in some numbers to kind of, I'll use just some really basic numbers. So we'll start with a 12 volt. We'll say on a 12 volt circuit, which is an automotive battery, we'll say 12.6 volts. And let's say my starter needs to draw 100 amps. Well, we can figure this out by using our math. We would divide 100 into the 12.6 volts to give me how many ohms would be in my starter. And if I press this equals button, you can see that the starter ohms are very, very low. They're not even a full ohm, right? They're 0.126, so very, very small amount of ohms in a starter. Well, what if this light bulb that we had, I'm going to clear these out, say I had a light bulb, and let's say that light bulb, I don't know how many amps your LEDs draw.
I think they draw 3 apiece. So if, let's say, I think in the bedroom I've got 4 lights at 3 amps. So
3 amps?
No.
For an LED?
Yeah, no, what is it?
I'd say 0.3.
Yeah, I think
like a quarter of an amp, let's say. Yeah. So we'll say a quarter of an amp, 0.25, right? Yeah. So then we can actually see that there's going to be 50 ohms in those light bulbs.
Okay.
Right? So if I applied 12.6 volts to 50 ohms, I would end up with obviously less amperage. The goal is, I would think the goal is that I would want to put energy efficient devices in my Skoolie, things like LEDs versus incandescent. Right?
Correct.
I'd want LEDs all day long so that I can keep my amperage very low. I want high ohm, good lumens. I want them to be bright, but I would want them to definitely give me that, that better power.
Right.
I don't want to have too much current.
All right. So another really important concept, I think, especially with Skoolies, is not the rock band, but the AC/DC part of it, because we're using both, many, but not everybody, but most, I think, are dealing with both systems within the bus.
Yes.
Because again, we're automotive kind of, but we're also sort of battery powered, but we're also want to use like the blender to make margaritas. So we got
That's important.
It's critical.
Yeah, it's critical.
So tell us the difference between AC and DC.
Well, the quick and dirty is DC. We'll start there. DC can be made from batteries, right? So it's chemical. When it comes to DC, the electrons move in one direction, right? And you're probably thinking, well, why would they move in any other direction? So they move in one direction.
It's our clock again.
Yes. And that's good, and that's good for electronics. So if I have things that need to communicate, or if I want to run a device like a camera, or if I want to run my laptop or whatever, it all has to run on DC. We want DC. DC is critical. It's important. It moves in one direction, as I said. It loses its energy, or it loses its ability to, it loses its voltage over distance. So in just inches, we're losing some voltage through voltage drop in the wiring. So it's not good for long distances. If I'm dealing with a Skoolie, how long is your Skoolie?
35 feet.
So you're going to have some loss or degradation
for
in your wiring. So DC is great for that because you're really not powering a lot. You're powering lights and that kind of stuff. But if you want long distance, especially when you have a power plant supplying a residential or a business or whatever application, we're going to want to have AC. So DC is great for automotive. It's great for smaller circuits like this, but we also have to have AC. Now, real quick, before we go forward, if you're ever going to measure this stuff, you're going to have a multimeter to do this. The symbol for DC is a solid line on top with 3 little dashes beneath. So whenever you're measuring electricity, and we can get into this later, you want to make sure that your meter is set to the right setting, because you can measure both. Typically, all multimeters will measure both types of voltage. So make sure you're on the right setting, so you're on that digital setting.
So the DC, yeah, so it goes, and it has, but you can run DC in 24 volt. I know I'm confusing
absolutely.
Things,
Yeah.
But so that's that's like me going to the river. I'm good going there like crazy.
Yeah, you move in one direction.
One direction, and then I get tired when I get to Bangor.
Yes.
Yeah. Okay.
That's exactly right. Great analogy. So AC is a wavy line. That's its symbol on your meter. So just in general. But if you notice that AC, the electrons move in 2 directions. So they cycle, they switch the directions. They constantly switch back and forth. And typically in the United States, it's a 60 cycles per second. We call that 60 hertz. So it's changing back and forth.
That's me working on the bus when I forget my tools.
Yeah, right. You're walking back and forth, and I forgot the wrench. Oh, where's my 10 millimeter?
How does it actually get there if it keeps going back and forth?
Well, it goes back and forth, right? It's cycling back and forth through that load.
Yep.
And as the electrons move back and forth, they keep re-amplifying themselves. So that voltage drop or line degradation isn't as prominent with AC. So AC is great for over distance. Right?
Which is why we have it in regular houses.
Yep, correct.
Yep.
It's perfect. And, the thing about AC, while AC is awesome in so many different ways where it can go over long distances, it's not really safe for electronics devices. You know, like anything with an integrated circuit, your cell phone, for example, or your camera or your laptop, right? We can't run those off of AC. And you're probably thinking, well, Tony, if we're plugging them into the outlet, they're on AC. Well, with this, with all your devices, you have a little box, and that little box is an AC-DC converter, right? We're changing the AC to DC. And you do that through a series of diodes. And a diode is a one-way check valve for electricity. It allows current to flow in one direction, but not the other. So if we put diodes in the way, we can make AC and change it just to DC.
Okay.
So.
And this is an important concept too, because if you're charged, if you're not plugged in anything, and so your bus is just, you're running off batteries, and you want to turn on your blender for your AC circuit, you need to have an inverter.
You need to have an inverter.
Correct. So that's what we need inverters for.
Yep, and you need to make sure that inverter is set to the correct wattage. Like,
Right.
what can it make? And you just brought up a great concept, wattage. We talked about volts, we talked about amps, we talked about ohms. Wattage is electrical power. So voltage is pressure, amperage is current, wattage is power. So wattage would be volts times amps. If I had a tire, right, and I wanted to pressurize my tire up to 32 psi, or whatever the label says on the door, right?
Yep.
That 32 psi would be the same as that 12.6 volts of your battery. I always like to use batteries and tires to kind of explain what I'm talking about, and they're both on the same thing, right? So my tire pressure is important. I got to have the right pressure. If I were to take a needle, which I don't want anybody to ever do, but this is an example. If I took a needle and I put it into the sidewall of the tire, you'd hear a little hiss sound, right? And that little hiss sound would be the air flowing out of that little hole. That air flowing out of the hole could be our amperage, to use our analogy. Right? So current, air flowing out would be the same as, current flowing out of the battery, right?
Yeah.
Now, that hole is going to be very small, which means it's going to probably take a couple of hours for that tire to go flat because it's seeping out. If I were to take a knife and stick it in the sidewall, it would go whoosh, the air would flow out a lot. That would be a lot less resistance, lots of current. So that's a good analogy when we use that amps, volts, and ohms. Now when it comes to wattage is power.
So if you had if you had a medium-sized hole in the tire, and we had a lot of pressure, now it's cramming through, you get some
You have an air compressor filling it as we go.
But as that tire got flatter and there's less pressure coming, or less volts, then you're probably gonna wind up with less total air coming out of the tire.
Yes, you'd offset it.
Offset it, right?
Yeah.
Okay.
So I guess.
And I'm thinking too, like, because if you're running all your power out of your 12-volt battery, it's just going to take a while to get to, if you need a lot of power, it's harder to get out of that battery. Whereas you got 110 coming into the shore charge, out of the shore power.
Yeah. Oh, yeah.
You got so much more power at your disposal.
I would want it plugged in. You're at the campground or wherever you are. You're plugging it into their power.
Yep.
You're getting their 110, right? We're not talking about an inverter right now. You should definitely use their power, because if you're running this off of an inverter, you're going to run your battery way down. Right. But the major difference, to kind of recap, DC is created from a battery. DC is okay for short distances. I would say inside of 30 feet is okay. Compensate if it's longer. AC is great for longer distances, and all of your appliances run off of AC. So you have to be able to have both. You need to be able to power both types of devices.
And you just can't store AC power. Really.
You cannot store AC at all.
Yeah,
you can store DC.
You store DC.
Which is awesome with DC. That's why.
So, actually, because that's perfect too, we want to talk about, you said because it doesn't travel over distance as well, let's talk a little bit about a voltage drop. Well, do we want to do that over there?
We can do that on the board.
Do that on the board. Yeah.
Do you want to move to the board at this point?
Sure, but actually, let's just introduce the concept first, because since that power is going to move from the battery to its load, and if it has to travel a long distance, it loses its power.
It loses its power.
So it's important to make that calculation, and you need a bigger hole in your tire if it's going to travel a long distance, right? You need less resistance, and you get less resistance by a bigger gauge wire.
Yep, bigger gauge wire, more strands of copper inside,
Right.
gives more highway lanes. If we were to equate electrons to cars, we have more lanes on the highway for them to travel down, and they can get to where they're going fast.
Absolutely.
Yep.
So I'll put a link in the description. So let's say, and what you need to know is that how long that power is going to go, and you have to take into consideration not only the power side but the ground side as well.
Correct.
And then you figure out that distance, how many volts you need, and you plug that into the calculator, and it'll tell you the wire gauge that you need. Because you don't, if it's, it won't power your devices if it's too much drop.
Yep.
And if the wire's too small, well, you're going to melt things.
Yeah, you want to make sure that it's super important. You want to make sure you have the right gauge wire.
Right.
And you want to think ahead too. If you're building this from scratch and you know that today all I'm going to do is lighting. Like all I need is lighting, so I'm going to use this little gauge wire. But then 2 years down the road, you want to have the inverter, you want to have the blender, you want to have
the
these
cell phone
motors,
charger.
the cell phone chargers, and there's more things you want. Try to think ahead. Don't think about today. Try to build it for the future scenario. Maybe it's a good idea to spend that extra money and get that thicker gauge wire, because those devices that you're going to run today, just lighting, will still work on a thick gauge wire. But if we build it for tomorrow, then we can add to it.
And for those of you doing buses, it's such a long, like to go to the back of the bus for the light flashers, that's great wire. It's like 12 gauge wire. And so, you can recycle a lot of that wire out of the bus when you're pulling it off. So.
Yep.